Hi, my name is Tim, and today we're going to talk about the buckling of thin-walled elastic structures. So the first question is, what's an elastic material? Well, at least in the context of quasi-static deformations, an elastic material is one that stores all the work you do on it. So this rubber band, for example, if I pull on it and release the force, it goes back to its original shape. So it's elastic. Now this wooden table is also elastic, but it's much stiffer than the rubber band. So when I press down on it, you can't see the deformations because they're only microscopic, but they're still there. Now this wooden dowel rod is also wood, but because it's so slender, it's easy for me to deform it. Now this toilet paper tube is made of cardboard, and it's similar to the dowel rod. So it can be strong or it can be weak depending on how it's loaded. If I load it like this, it's obviously very weak. But if I can just try to pull it or push on it, it can be very strong. So here's an example here, just 4 ordinary paper towel tubes, and this is a stiff placemat. And here's a 10 kilogram weight. For the Americans in the audience, this is 22 pounds. And I can put that right on top of the paper towel tubes, the toilet paper tubes, and it holds the weight with no problem, even though this is incredibly light. So thin-walled structures like this are very useful in building because they're so light and yet so strong. But they're only strong in a certain sense. Now, nature wants the structure to bend as opposed to stretch. So the strain energy can be broken up into 2 pieces. A term that involves all the bending energy, which corresponds to a change in the curvature tensor for a surface, and the stretching energy, which corresponds to a change in the metric tensor. But there's a small parameter in front of the bending term, so it's more economical for nature to put the energy there, so to speak. So the structures want to bend as opposed to stretch. So if we come back to the toilet paper tube, I have a tangent plane here I can indicate with this piece of paper. So if I can load this tube tangent to its surface, then it will be strong. Okay? But if I load it this way, like I did with the weight, then it's going to crush the structure. Okay? So when you're building an elastic structure, you want the loading to be done tangent to the surface. And that's what we have here. The load is all tangent to the surface. Okay? Now, we have a very light structural member holding up a great weight. Right? But nothing in life is free once you leave your parents' house, right? So what do we have to pay for this? Well, if one of these members were to fail, then the entire structure will fail catastrophically. And one of the ways that a structure can fail is to fail by buckling. And that's what we're going to talk about now.
The simplest kind of buckling is Euler column buckling. Imagine a straight elastic column with a constant cross-section, and imagine that a compressive load P is applied to the top of the column. For small loads, the column remains straight, but for larger loads, the column buckles or bends considerably. Here you can see a dowel buckle under a very light load. A hollow tube can buckle like an Euler column if it's long enough, but the short toilet paper tubes tend to buckle in a different way.
Now we've set up our 10 kilogram weight on 2 paper towel tubes, and you can see they're already starting to buckle here and here. And if I give them a little push, then we have catastrophic failure. And this is what those 2 tubes look like after they've buckled.
Let's review a mathematical model for Euler column buckling because it's relatively simple. A model for the buckling of a toilet paper tube, in contrast, will be much more difficult, so we'll forego that in this video. Let's develop the equations for determining the buckling load of a column. We'll parameterize the bar with respect to arc length, called S, and assume that the bar is inextensional. For a slender bar with no load applied, let alpha denote the angle that a tangent makes with the horizontal. Now apply a force factor to deform the bar. The new angle is psi, and if x and y denote a point on the deformed bar, then dx ds is cosine psi and dy ds is sine psi. We'll go through the details a little quickly, but I hope that there's enough here to guide the interested viewer through the calculations. The governing equations are shown, where little h and little v are the components of an applied force per unit length of the bar. E is Young's modulus, which indicates the stiffness of the material of the bar. For a vertical column, alpha is pi over 2. Since the applied force is only downward at the top of the column, we set the horizontal component little h to 0 and little v to be minus p delta of s minus L. P is going to be the magnitude of the applied load, and delta is the Dirac delta function. It's then convenient to let phi be the complementary angle to psi. So phi is pi over 2 minus psi. And in this case, we obtain three governing equations that you see. Note that they are all nonlinear, which in general makes them very difficult to solve. Now we can employ different boundary conditions, but let's assume for the sake of simplicity that the column is fixed and fixed so it can't rotate at s equals 0. So x of 0, y of 0, and phi of 0 are all 0. If the column is free to bend at the top, then the derivative of phi with respect to s is 0 at s equals L. Note that the trivial solution, that is, phi equals 0, x equals 0, and y equals s, satisfies the ordinary differential equations and the boundary conditions. So buckling occurs when that trivial solution fails to be unique. Since the equations are nonlinear, they are difficult to solve. But if phi is small in magnitude, then the sign of phi is approximately phi, and we obtain a linear equation for phi that we can solve using the methods of a first course in differential equations. We find that phi is equal to some constant c times the sine of the square root of p over ei times s. This satisfies the differential equation for phi and the corresponding boundary conditions for all constants c, provided that p has the special value of pi over 2 quantity squared times ei over L squared. That is the buckling load for the column. Now there are other mathematical solutions for larger values of p, but they are not realized physically. Now it's one thing to compute the buckling load, but it's another to watch the buckling occur in an animation. In this animation, the load is not quite vertical so as to introduce an imperfection. Note that the column remains straight for small loads, but as p increases, the beam bends dramatically near 2.47 ei over L squared. Now in practice, at this point, the beam may break or become plastic, so let's assume that it doesn't so that we can relax the load and then watch it buckle a second time. The second time, the animation will pause near the buckling load before proceeding. Now note in the animation that the length of the arrow corresponds to the size of the load that's being applied. Now as we approach the buckling load at 2.47 ei over L squared, note that the beam is not perfectly straight when it starts to buckle. That again is a result of the imperfection introduced. But that's okay, because in real life, there are all sorts of imperfections. A static way to observe buckling is to plot the displacement of the top of the column as a function of the load. Here we see that the displacement is very small until the load gets close to the buckling load, where it increases dramatically. Now in the previous example, we assumed that the column was free to bend at the top. However, it's important to note that the boundary conditions can have a dramatic effect on the buckling behavior. Suppose instead that phi is 0 at s equals L instead of the derivative of phi with respect to s. This results in a buckling load that is 4 times higher than before. Let's watch an animation of this scenario. Note that the column buckles near 9.87 ei over L squared instead of 2.47 ei over L squared, and the shape of the buckled column is dramatically different. The mathematical analysis of buckling can be quite complicated, so if you aren't already convinced of that, let's examine one more case. Let's determine the height of a column for which it buckles under its own weight. In this case, little v of s is minus rho GA, where rho is the density of the material, A is the cross-sectional area of the column, and G is the acceleration of gravity near the surface of the Earth. Big V of s is minus rho GA times L minus s. The resulting linearized differential equation is difficult to solve in spite of its being linear because of the s term that appears explicitly in the equation. So with considerable difficulty, we can write phi as a linear combination of two Airy functions, and by applying the boundary conditions, we obtain a condition for buckling that involves another special function called a regularized confluent hypergeometric function. From this, we can deduce the critical height of the column to be 1.99 times the cube root of EI over rho GA. So if your brain doesn't hurt yet, then I encourage you to investigate other buckling phenomena on your own. If your brain does hurt, then take a few minutes to relax.